Hello everybody. We were discussing memory, and in the last class we got introduced to a memory organization where we had noted that each individual memory cell are the ones where the digital information is stored, okay, in the form of 1-bit information. Okay. So, in this class we shall look more into these memory cells, and we shall look into this BJT bipolar junction transistor based memory cell, as well as CMOS and standard MOS based memory cell. Okay. And what we have taken up is called static RAM. Random access memory you have already seen. Static we have already defined in the last class, that static RAM is the one where the periodic refreshing is not required, and we shall discuss the other type of RAM also called dynamic RAM or DRAM, okay, in subsequent class. And at that there we shall see that in that DRAM based memory organization, the information is stored in a capacitor which could be leaky, which essentially is leaky. So, it requires periodic refreshing. Okay. In static RAM, the one that we shall be discussing now, that is not there. Okay. So, you do not require that kind of thing, but in DRAM the number of parts required is less. Okay. So, here the number of transistors and other things, these circuit elements will be a little bit more. So, in DRAM the packing density will be a little bit what is that called, more. But here SRAM it will be faster, and it is this refreshing is not required. So, these advantages are there. Okay. So, more of DRAM we shall see later. So, today we discuss this static RAM memory unit, and more specifically the memory cells. Okay. So, here we begin with the BJT based this memory cell. So, we had seen some such organization before, right. We had seen a memory cell in the last class, if we remember, and this memory cell had two lines. Now, we have redrawn it in a little bit different manner. So, this is one line D, another is D prime, that what you see basically. So, from each memory cell two lines are coming out. Okay. It can be also called bit lines. So, one bit, so this is data and this is data bar, one is opposite of another. Okay. So, this is what we note. Okay. Other than that, what we see, this is X and this is Y. So, basically these are the addressing of a particular location in the memory block. So, this is coming from row, and this is a matrix based arrangement, okay, matrix based addressing. So, it is coming from a row decoder. So, this is the row line, and this is coming from a column decoder. So, this is the column line. Okay. So, for which when both of them are activated, so this particular cell is addressed. Okay. So, other than that, what we see, this is what we had seen before. What we see that there is a control logic block. So, this control logic block is similar to what we had seen before. In addition, we have got a data in input. Okay. So, this is chip select, and this is read or write operation that we are doing. Other than that, what else we see? This is a write amplifier block. So, when you are writing it, so this is some additional circuitry which actually making it happen. Okay. So, we shall analyze it, we shall see what is there inside. Okay. And then we have got read amplifier. So, this is the read or sensing amplifier. So, what is there in the cell that we would like to sense and make it available to the outside world. Okay. So, this is the atypical SRAM memory block, and we shall move forward, and in the memory cell we shall see that it is there is a multi-emitter transistor pair connected in a cross coupled mode, and which is operating in a bistable mode as well, that is either it is one transistor is on or it is off, okay, and the corresponding transistor will be in the opposite state. If one is on, another will be off. So, let us see. Okay. So, this is the basic memory cell, right. More of it, how it gets connected to the other part, that is sensing amplifier, write amplifier and all those things, control logic, we shall see in subsequent slides. Okay. So, this is the multi-emitter transistor pair that we are talking about, and you see that they are connected in a cross coupled mode. So, each one of them as such can be considered as an inverter, right. And this is the column and this row and column address the select line. Okay. And when they are not selected, the value are 0. Okay. And if they are selected, value is 1, that is high. So, otherwise it will be low. Okay. And this is the line that is going to those data and data bar bit lines, right. So, this is ED0 and ED1 that you see over here. Okay. And other important thing that we note here, that in a BJT based circuit, so whenever the transistor or the one that is driving it, it is a logic low. Okay. So, the value is 0.3 volt or less. So, saturation will be 0.1, 0.2 or even lower depending on the level of saturation. So, logic low that is placed over here can be considered as less than 0.3 volt. Okay. And logic high we have seen before, if it is a TTL based circuit or this transistor the operation. So, we can consider this to be greater than 3 volt when it is logic high. Okay. So, other than that, we take note of that these lines, okay, has a bias voltage connected through a power supply and a resistance. We shall see that circuit little later, for which 0.5 volt is presented over here. 0.5 volt, okay, is presented here. And now, depending on amount of current, etc., flowing, small drop might be there, but otherwise it is 0.5 volt. Okay. So, when these are low or any one of them is low, this x or y are low. Okay. So, this is 0.3 volt, right, and this is 0.5 volt. So, current will not be flowing in this direction. Is it clear? Right. So, at that time, this particular circuit, right, this emitter, this ED0 and ED1 is not contributing in any way, electrically not contributing. Okay. And these are remaining at when these are remaining at 0. So, the current will be flowing in this direction, in this manner. Okay. This is the first thing that we observe. Next is these two transistors, can both of them be on or both of them be off? Okay. Now, if you investigate, you can see that both of them on or both of them off is not possible. Okay. So, if say this is on, then what is the voltage over here? This is ground. So, this will be here on means it goes into saturation. So, this RC, right. So, this is say 0.3 volt or so, 0.2 volt, whatever is the saturation value. So, that will not be enough to drive it on. So, that is a small voltage, it is not more than the the base emitter voltage that is required, 0.6 volt or 0.7 volt. Okay. So, this will be off at that time. If it is on, this is off. Okay. Similarly, if it is off, then this is not conducting. So, this is the voltage will be high. So, sufficiently high. So, that will be 5 volt to drive it deep into saturation and vice versa. Is it clear? Okay. So, one of them need to be off and one of them need to be on, and as long as this is remaining at 0 and also this is what is happening. And how to switch them, if say Q0 is on, right, and Q1 is off, how to make Q0 off and Q1 on, okay, in the right operation, that we shall see little later. Is it fine? Right. This part is the major thing, and this is similar for your MOS based cell or CMOS based cell also, where two inverters will be connected back to back in a cross coupled manner, rather like this, with we can see the feedback coming in this manner, right. So, similar thing will be there for the other cases, which will offer a bistable mode of operation for this particular block, right. Fine. So, when both of them are high, this x and y are high, that means this memory cell is now accessed. Okay. So, when these are high, so basically this particular line will be now operative. So, the current now will be flowing, because this is a during read operation 0.5 volt or so. Okay. Write operation we shall see what is happening at that time. Okay. So, the current will be directed in this direction. So, we consider for our general discussion that Q naught is on, okay, and Q1 is off. Okay. The similar discussion, I mean, this is just analogous. So, if it is otherwise, the similar analysis will follow, okay, just which is almost which is equivalent for whatever we discuss for Q naught being on. Okay. Now, we look at reading from the cell. So, so the cell is already presented here. So, this is the cell that we had seen before. So, this is Q naught. So, this is on now and this is off, right, and x and y we have made it high. So, this is high and this is high, okay, more than 3 volt or so, right, and this is the bias voltage has been kept in the 0.5 volt. So, this is the bias voltage that I was talking about, right. Okay. So, now this transistor is on. So, this emitter, from this emitter the current will flow in this direction, right, and this transistor is off. So, no current is flowing. So, no current is flowing in this direction. From through ED1 no current is flowing because this transistor is off. Is it clear, right? So, now this current that is flowing, right. So, when it passes through this Q2, so the Q2 will become on, and in this case this Q3 no current is flowing. So, Q3 will be off. So, when Q2 is on, this D out will be low. Okay. So, this will be low and this will be high. Is it all right? So, Q naught is on, then the data read through D out is high. So, that means a storage of 1 is there for such configuration, on and off. Is it clear? In contrast, had been the case that this is on and this is off, okay, then current would have flown in this direction, this is right, okay, and it would not have flown in this direction because this is off. So, this current is flowing in this. So, this will be on and this will be off. Sorry, not this one, this will be off, right. So, this one will be high and this one will be low, right. So, Q1 on is, then data out is low, and Q naught on is data out is high. Okay. So, this is the way we can visualize that storage of information and the reading that is taking place. Is it fine? Okay. Now, we look at the writing operation. Okay. So, the circuit that you can see now, this is the basic memory cell, okay, and generally we consider this is on, Q naught is on and Q1 is off, right, and this is the data line or the bit line, okay, and this is the reading or sense amplifier. So, this is D out bar and this is D out, which we have already seen. Now, here in this place we are having this particular block. Okay. So, this is extended to this particular side. Okay. Now, what we have got here? So, we can see that there is this read write logic, control logic is there, chip select is there, and data that we want to write, okay, that is also there. Fine. Now, if chip select is high, then this cell is neither read nor written into. Okay. So, if chip select is high means this is 0, okay, and so and there are other circuitry also to make this particular thing tri-stated. And when chip select is low, so then this is 0, so this is 1, okay. And at that time, if this read write bar input is high, okay, so this is your high, okay. So that is read operations, that is relates to read operation. So this is your 1 and this is your 1, okay. So this is your so this one will give you a 0 over here. Is it clear? Okay. So this 0 will generate for this NAND gate output A1 and it will generate output, this is 1. Please understand. Okay. So chip select is 0 and read write bar input is 1. So what we are having? We are having a 1 1 over here, irrespective of whatever be the value of D in. Okay, because this read input 0 means read input 1 means this NOT gate output is 0 and corresponding these two NAND gates output will be 1. This part is understood. Okay. Then rest of the thing is, if then this is high and this is high. So these two transistor Q4 on and Q5 on. Okay. So this voltage over here is very small. This voltage here is very small, 0.3 volt, 0.2 volt, 0.1 volt of that range. Okay, right. So then this diode is off. This diode is off. So this part of the circuit. So this part of the circuit, as if it is not there. Okay, because no current is flowing from this direction, and it is diode is, current can flow in only one direction. So it is not also, it is not possible to flow current in the other direction as well. So it is what we had seen before. So standard read operation that would take place. Is it fine? Now we go to the other option. So now this read write bar input is 0. Okay. So this is 1, chip select is 0. So this is 1. Okay. Now if D in is low, so that is 0. Okay. Then this is also 1, this is NOT gate, so this is 1. So this NAND gate output will be 0 and this NAND gate output will be 1. Is it clear? This part is understood. Because of which this VB, this particular base voltage of transistor Q5, okay, this is high and this is low. What does it mean? So this will be on, so this voltage will be low over here and this is low, that means this transistor is off. Okay. So this voltage over here is high. Now this diode conducts. High means close to VCC, close to 5 volt, depending on how much IC/RC drop will be there, right? And there is a 0.7 volt drop over here. So now this voltage is much larger than what we had seen before. Okay. So this so there is a path over here, there is a path over here. So rest of the voltage drop, current drop will be over here R2. Okay. So that is what you can see now, that this voltage is now held at high. What about the other side? This one, it is still at low because this transistor is at off. So this side you have got, this is now high, this ED0, and this ED1 is at low. Okay. And EC0, ER0, this EC1, ER1, they are all high because this particular cell is addressed. Okay. Now when this thing happens, Q0 which was on and Q1 which was off, now this is, and it was just holding one these cross coupled structure. If one is on, it remains on, another is off means it remains off. So that was the case at that time. Now because of these external forcing inputs that you get over here, that this is high and this is low, what would happen? So, this transistor now cannot conduct in this direction. Okay. So, this transistor will go off and it raises the voltage over here. Okay. So, that voltage will allow this transistor to go on, right, and this is low, there is no issue, it is possible. So, Q naught now will go off, okay, will become non-conducting, right. So, Vc 0, so Vc 0 is this voltage will go high, right, which will make now Q1 on. Okay. So, Q naught which was on now becomes off, right, and Q1 becomes on. Okay. After, if you stop the write operation and the circuit goes back to its normal state. Okay. So, both of them are say 0, this address is not invoked. So, this cross coupled nature will keep Q1 at on and Q naught at off, the way it was happening before. For Q naught which was on was remaining on and Q1 which was off was remaining off. Okay. So, similar thing will happen here, it will remain stable, and as I said, it does not require refreshing, and also basically they are holding each other in a stable mode. Is it clear? Right. How the switching is taking place within the memory cell, for which was the transistors now are switching, changing their on or off value, and if Q naught on was logic 1 stored or value 1 stored, binary value 1 stored, then Q naught off is binary value 0 stored, the way we have seen before, and if we now do the reading, we will see that 0 was there. So, 0 will be read now at the D out over here after this operation. Okay. And instead, if D in was high, okay, then what will happen? So, D in was high means this would have been low and this would have been high, if this was high. Okay. So, this is high because of this read and CS inputs. Okay. So, this is low means this is high means this is conducting. So, this part is low. So, this is not conducting, and this is low means this is not conducting. So, this is high. So, this output will become high means this is high. So, this will become high and this will become low, right. That means Q2, Q1 will not conduct and Q naught will conduct, so which was the previous case. As such, Q1 is not conducting because this transistor is off. So, it will continue to remain its previous value, which was a logic 1, a binary value 1 that was stored in this particular cell. Okay. Is it clear? Right. So, this is how it is taking place in writing operation. Now, we look at, so BJT, if you have understood, similar thing is there for other types, CMOS based or MOS based SRAM, static RAM. Okay. Only that the way the current is driven, etc., those things are, because it is a field effect device, those things are a little different, but basic understanding remains the same. Okay. So, here we see one typical SRAM CMOS. Okay. So, this is the this is PMOS and this is NMOS, PMOS, NMOS. So, one CMOS inverter, this is another CMOS inverter, and this is again connected in a cross coupled manner. And we know that from the previous discussion, if one is on, then the other one need to be off. Okay. Right. So, if this NMOS is on, then this NMOS need to be off. Okay. And the way the BJT connection was there, right, and vice versa. If this is on, this will be off. Okay. Is it clear? Right. And when this X and Y are low, then it will maintain its state. Okay. Now, when this is coming from the column address, right, row and column address. So, these are the data lines. Now, what you see that this X is the row address, okay, coming from row address decoder. So, these transistors Q5, Q7, Q9, Q6, Q8, okay, all these are pass transistors. Okay. Pass transistors means if the input is high, then you have a channel getting formed. So, basically source and drain there is a very low resistance path. So, one is getting connected to the other. So, information value signal moves from one side to the other side. Okay. So, that is the the pass transistors that we are talking about. Okay. And so, whenever this x becomes high, right. So, the Q5 and Q6 makes data available to this data and data bar lines, the bit lines. Okay. So, these are the providing access to the data lines. Okay. So, this overall this thing, this memory cell and two of these transistors providing access to the data line. Okay. So, they are often pulled together and termed as 6 transistor configuration for, this arrangement is called 6 transistor configuration for CMOS SRAM. Okay. So, 1, 2, 3, 4, 5, 6. So, these are the 6 transistors. Is it fine? Right. So, when x and y are low, so the circuit is not addressed. Okay. So, it is storing because it is in bistable mode whatever information it had, and for read operation, right. So, both x and y are high, right, and this now if see this is read bar and write. Okay. So, this is has to be low for read operation. So, basically then this is a pass transistor. So, D in is not allowed to go in that direction. Is it fine? So, at that time whatever information is there here in the data bar, right. So, this y is high. So, this is getting passed from, by the pass transistor Q8, right, and then this is a CMOS inverter. So, whatever is the data bar, its inversion is available as D out. So, if Q0, Q1, Q2 pair, this one, so this Q2 is on, okay, that means the output will be your high, okay, and if this is off, the output will be low. Is it clear? Right. Now, how the write operation takes place? Again, these two address should be high. Okay. Chip select wherever it is providing access to this particular chip, that should be at a proper value. Okay. Now, this is 1. So, D in is allowed to enter, right, and when this D in comes here, again this is a forced input, which is and for which this particular output will be of a say high value. So, if it is sending a high, okay. So, this high will make this one on, right, and that will make it off, okay. This value will be low. So, this low will make this is off, right, and will remain at high. Then if you remove it, because of its bistable nature, it will continue to remain this value. So, that is getting switched, okay. So, accordingly this switching will take place, right, and for writing a 0, so this will be low. So, this value will be low at that time, okay. So, which will force this one to be on and this one to be off, okay. So, this is one typical arrangement, okay. Finally, MOS based SRAM. Okay. So, in MOS based SRAM, it is compared to BJT based memory cell that you had seen. Okay. So, we had these 2 transistors there, inverter, and here instead of normal transistor, normal resistor, you can have MOS based transistor, which is MOS based resistance made, which takes less space. Okay. Otherwise, one can make a normal transistor, normal resistor also in this place, and this will also provide the same cross coupled bistable mode of operation. Cross coupled inverters providing bistable mode of operation. Okay. So, if these are again loads are made using MOS based transistor. Okay, then you have got 1, 2, 3, 4 and these 2 providing access. So, 6 transistor configuration, okay. And if these are replaced by normal resistance, right, which will take more space and all, a bit difficult. The kind of packing density that these MOS based devices provide, it will not be able to get its optimal uses. So then that will be called 40 configuration or 4 transistor configuration. Okay. So this is one typical organization, and if you look at it, you can see there are A0 to A5, so 6-bit address. So 6-bit address 6 to 64 address decoding, that is what is happening. Okay, so 64 rows, right? Here also 6 is there, so 64 rows, right? So 64 into 64, so 4096 words are there, and in each place you are storing 1 bit of information. So this is a 4096 words, 4096 into you can say 1 bit MOS RAM, okay, MOS SRAM, okay. This is bit organized. Is it fine? Right. So and this is matrix addressing, right? Fine. So with this we conclude, and what we have seen very quickly, that static RAM or SRAM can be made with BJT MOSFET CMOS, okay, and in each case we are looking at cross coupled inverters made up of transistors, and they are operating in bistable mode. And for BJT we have seen how the sense amplifiers and write amplifiers work. Similarly, we had seen it the CMOS and normal MOS, the uses of pass transistors for reading and writing operation. Okay. Thank you.